Exponential equations with logs. There's our log. We want to take the log of both sides of an equation when we don't have a common base. So for instance, 2 and 8 have a common base, right? 8 can be written as 2 to the third. 2 is already written as in reduced form, so 2 and 2 to the third, they have a common base. But what if we were talking about 3 and 6? You can't write 6 using 3 as a base. For instance, 3 to the second would be 9, so that doesn't work. So you would have to take the log if you had 3 and 6 for your two bases. Alright, so logs move the exponent in front of the number. I'll show you what I mean. So let's say we had, for an example, we had 2 to the x equals 5. Now we can both agree that 2 and 5 cannot be written with the same base. In other words, 2 to the second is 4, 2 to the third is 8, so 5 can't be written with 2 as a base. So now I have to take log. So I'm going to do log to both sides. So I would do log 2 to the x equals log of 5. And on step 2, where it says logs move the exponent in front of the number, here's our exponent. I'm going to move that in front of the number. So it's really going to read this. It's going to read x log 2 equals log 5. And just like if you had, for instance, 2x, we know that that means 2 times x. It's understood. When a number and a letter are written next to each other, they mean multiply. What's the same way with logs? So x log 2 really means x times log 2. So I want to solve for x, so that means I want to get x by itself. So if I'm multiplying by log 2, I just divide by log 2. And then I'm on step 3 now in my notes. It says use 4 decimal places for logs in order to be accurate. So now it's just a calculator equation. So we write x equals, and we get our calculator out, and we type in log 5. And when I typed in log 5, I got 0.69897, and if for 4 decimal places, that 7 rounds the 9 up to a 10. So that's really going to be not 89, it's going to be 90. So make sure you're rounding correctly. Over, and then if I type in log 2, I get 0.30102. That 2 tells us to keep the 0 the same, so it's just 0.3010. And now I'm going to divide those out, and I'm going to get 2.3219. And all this is saying is that 2 to the what power gives me 5. That's how this question reads. 2 to the what power gives me 5. And looking at that, just to estimate, I know 2 to the second would be less than 5 because it's 4. And I know 2 to the third would be greater than 5 because it's 8. So I know that my answer is going to be between 2 and 3 because of the 2 there and the 3 there. So look at my final answer. I got 2.3. That's really close. That sounds good. And actually it's closer to the 4. 4 is closer to 5 than 8 is to 5. So it would make sense that it's less than, it's 2.5 or closer to 2. All right. Let's try one a little more complicated now. All right, solve for x. 6 to the 3x equals 5. We can't find a common base. Neither of these are perfect squares or perfect cubes, so we can't break them down anymore. So we need to take the log of both sides. So it's going to be log 6 to the 3x equals log 5. Remember, whatever you do to one side, you still have to do to the other side of the equation. And now remember what logs do? They move that exponent in front of our log. So it's really going to read 3x times log 6 equals log 5. And my goal is to solve for x, so I'm multiplying by 3 and I'm multiplying by log 6, so I want to divide by both of them. I can do that all in one step. So I can divide by 3 to cancel the 3's and log 6 to cancel the log 6's. But I need to make sure I do the same thing over here. So I'm dividing by 3 log 6 on the other side. And now it's just a calculator problem. I'm going to type in log 5. And when I do, I get 0.69897. We talked about that same one earlier. It really becomes 0.6990. And then I can type in 3 log 6. It's really 3 times log 6. But if you type in 3 log 6, your calculator knows it means multiply. And we get 2.33445. That 5 rounds the 4 up to a 5. And now I just divide them out. So 0.6990 divided by 2.3345. And I get about 0.2994. And now that I have my answer, I'm just going to see if it's reasonable. This is saying 6 to the something power equals 5. Well, 6 to the first power is going to be a number bigger than 5. 6 to the first power would equal 6. So I know that my number has to be less than, my exponent actually has to be less than 1. So, and it's being multiplied by 3, so it really has to be less than 1, right? That tells me it has to be less than a third, because a third times 3 would give me 1. So that just helps you realize that, hey, I'm working for a number that's less than 1, and we have it. So it's a good idea to estimate afterwards. All right, let's step it up, do one a little bit harder, so you're ready for anything, any log that can be thrown your way. Too many logs, don't know what to do. All right, the happy one can stay. So we're going to solve for x. And our question is 2 to the x power times 1 over 32 equals 16. All right, we haven't talked about getting the same base whenever you have the base on the bottom. But we do know about negative exponents, right? So all I'm going to do is look at that 32, and I'm going to do this off to the side. 1 over 32, I need the base to be 2, because that's my smallest there. So let's see if we can get the same base. So this one actually may not require logs if we can get the same base. So 32 can be 2 to the what power? Well, 2 to the third is 8. 2 to the fourth is 16. Oh, so 16 can be 2 to the fourth. So 32 is 2 to the fifth. So this really is 1 over 2 to the fifth. Now, I don't want it to be a fraction, so how do I make it not a fraction? Well, remember, if it's positive, it's happy, but if it's negative, it's unhappy. So we can actually make this negative by putting it to the top. So negative 5. So it's going to be 2 to the negative 5 power. So it really reads 2 to the x times 2 to the negative 5 equals 2 to the fourth. So we do have the same base on this one. So since we have the same base and we're multiplying here, we can just add the exponent. So it really reads 2 to the x minus 5. We can just add those together equals 2 to the fourth. And now since we have the same base, we can set the exponents equal to each other. So it's just x minus 5 equals 4 plus 5, and x equals 9. So that one didn't require logs, believe it or not. Yeah, he believes me.